In the previous videos, we put together almost all the pieces you need in order to implement and train a neural network. There's just one last idea I need to share with you, which is the idea of random initialization. When you're running an algorithm like gradient descent or also the advanced optimization algorithms, we need to pick some initial value for the parameters theta. So for the advanced optimization algorithm, it assumes that you will posit some initial value for the parameters theta. Now, let's consider gradient descent. For that, we also need to initialize theta to something, and then we can slowly take steps that go downhill using gradient descent to go downhill to minimize the function j of theta. So what can we set the initial value of theta to? Is it possible to set the initial value of theta to the vector of all zeros? Whereas this worked okay when we were using logistic regression, initializing all of your parameters to 0 actually does not work when you're training a neural network. Consider training the following neural network, and let's say we initialize all the parameters in the network to 0. And if you do that, then what that means is that at the initialization, this blue weight, I'm coloring in blue, is going to equal to that weight, so they're both 0, and this weight that I'm coloring in red is equal to that weight, which I'm coloring in red, and also this weight, which I'm coloring in green, is going to equal to the value of that weight. And what that means is that both of your hidden units, A1 and A2, are going to be computing the same function of your inputs, and thus you end up with, for every one of your training examples, you end up with A21 equals A22. And moreover, because I'm not going to show this in too much detail, but because these outgoing weights are the same, you can also show that the delta values are also going to be the same. So concretely, you end up with delta 11, delta 21 equals delta 22. And if you work through the math further, what you can show is that the partial derivatives with respect to your parameters will satisfy the following, that the partial derivative of the cost function with respect to, I'm writing out the derivatives with respect to these two blue weights in your network, you find that these two partial derivatives are going to be equal to each other. And so what this means is that even after, say, one gradient descent update, you're going to update, say, this first blue weight with learning rate times this, and you're going to update the second blue weight with some learning rate times this. But what this means is that even after one gradient descent update, those two blue weights, those two blue colored parameters will end up the same as each other. So there'll be some non-zero value now, but this value will equal to that value. And similarly, even after one gradient descent update, this value will equal to that value. There'll be some non-zero values, just that the two red values will equal to each other. And similarly, the two green weights, they'll both change values, but they'll both end up the same value as each other. So after each update, the parameters corresponding to the inputs going to each of the two hidden units are identical. That's just saying that the two green weights are still the same, the two red weights are still the same, the two blue weights are still the same. And what that means is that even after one iteration of, say, gradient descent, you find that your two hidden units are still computing exactly the same function of the input. So you still have this A12 equals A22. And so you're back to this case. And as you keep running gradient descent, the blue weights, the two blue weights will stay the same as each other, the two red weights will stay the same as each other, the two green weights will stay the same as each other. And what this means is that your neural network really can't compute very interesting functions, right? Imagine that you had not only two hidden units, but imagine that you had many, many hidden units. Then what this is saying is that all of your hidden units are computing the exact same feature. All of your hidden units are computing the exact same function of the input. And this is a highly redundant representation, because that means that your final logistic regression unit really gets to see only one feature, because all of these are the same. And this prevents your neural network from learning something interesting. In order to get around this problem, the way we initialize the parameters of a neural network, therefore, is with random initialization. Concretely, the problem we saw on the previous slide is sometimes called the problem of symmetric weights, that is, of the weights all being the same. And so this random initialization is how we perform symmetry breaking. So what we do is we initialize each value of theta to a random number between minus epsilon and epsilon. So this is a notation to mean numbers between minus epsilon and plus epsilon. So my weights or my parameters are all going to be randomly initialized between minus epsilon and plus epsilon. The way I write code to do this in Octave is I might set theta 1 to be equal to this. So this rand 10 by 11, that's how you compute a random 10 by 11 dimensional matrix, and all the values are between 0 and 1. So these are going to be real numbers that take on any continuous values between 0 and 1. And so if you take a number between 0 and 1, multiply it by 2 times in the epsilon, then minus in the epsilon, then you end up with a number that's between minus epsilon and plus epsilon. And incidentally, this epsilon here has nothing to do with the epsilon that we were using when we were doing gradient checking. So when we're doing numerical gradient checking, there we were adding some values of epsilon to theta. This is a unrelated value of epsilon, which is why I'm denoting init epsilon, just to distinguish it from the value of epsilon we were using in gradient checking. And similarly, if you want to initialize theta 2 to a random 1 by 11 matrix, you can do so using this piece of code here. So, to summarize, to train a neural network, what you should do is randomly initialize the weights to small values close to 0, between minus epsilon and plus epsilon, say, and then implement backpropagation, do gradient checking, and use either gradient descent or one of the advanced optimization algorithms to try to minimize j of theta as a function of the parameters theta, starting from this randomly chosen initial value for the parameters. And by doing symmetry breaking, which is this process, hopefully gradient descent or the advanced optimization algorithms will be able to find a good value of theta.